Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirabbil alamin wa bihi nasta'inu ala umurid dunya waddin sayyidina wa maulana Muhammadin wa ala alihi wa sahbihi ajmain. Amma ba'd. Your Honorable Dr. Anton Prasetyo is my advisor. Your Honorable Mrs. Eni Yulianti, MSI as the examiner. Your Honorable Mrs. Anik Mawanatin, MP as the consultant. My name is Fikri Haikal, and in this great opportunity, I would like to present to you my research proposal, synthesis, and characterization of lanthanum top strontium bismuth titanate using molten salt method. First of all, I would like to explain to you the outline of this presentation. The first one is introduction, the second one is objective, the third one is methodology. We have a problem that we are already facing right now. One of them is water pollution. The main source of water pollution is textile industry, house activities, and pulp and paper industry. Water pollution can affect us in many ways. The first one is polluting the water bodies. The second one is it can disrupt the existing ecosystem around it, and it can also cause sedimentation in the riverbanks, and also it smells. So what are the solutions for this problem? The first one is using adsorbent. The second one is using chemical degradation. The third one is using biological degradation. The last one is catalytic degradation. But using adsorbent to this problem produces another problem because using adsorbent produces sludge. The same result is also achieved by using chemical degradation, in which it also produces secondary pollutant. Meanwhile, biological degradation does not produce any other waste, but the most pollutants are stable and resistant, and that's why biological degradation is not suitable to be used in handling this problem. So let's take a look at photocatalytic degradation. So it has some advantages over some other method. The first one is because it uses sun's energy, and the second one it has high activities, and the third one it's stable. Because it's stable, it can be reused again and again and not producing any other waste. As Allah said in Quran Surah Al-An'am ayah 141, Bismillahirrahmanirrahim. Wa huwa alladhi ansha'a jannatin ma'rushatin wa ghayra ma'rushatin wan nakhl. Wa ghayra ma'rushatin wan nakhla waz zar'a mukhtalifan ukuluhu waz zaytuna war rumman mutashabihan wa ghayra mutashabih. Kulu min thamarihi idha athmar. Kulu min thamarihi idha athmar wa atu haqqahu yawma hasadih. Wa la tusrifu innahu la yuhibbul musrifin. Allah particularly said in this ayah that we are allowed to consume what Allah provide to us by using words kulu. But He also warns us by using words wala tusrifu. Be not excessive or don't be overconsume something that Allah has provided us, because innahu la yuhibbul musrifin, because Allah does not like those who overconsume. And the example of overconsume is like we said earlier, that something that we overconsume can cause pollution, can cause another disruption in our environment. And so by doing this research, hopefully we can minimize that effect, or also we can prevent it to be happen in the future. So our material is strontium bismuth titanate. So it has a good potential as a photocatalyst. Here's the structure of strontium bismuth titanate. Why is it good as photocatalyst? Because it works on visible light. It has good activity on degrading organic solution. It is stable and reusable. But it also has some defects because it's not well researched. It has recommendation activities, and although the it can work on visible light, the band gap energy is close to UV range, so it's not very good. Here's the graph that shows the band gap energy of strontium bismuth-titannate. And here's the graph that shows the photocatalytic activity of strontium bismuth-titannate on degrading metal orange solution. We know that in the time frame of 200 minutes, more than 90% of metal orange is degraded by strontium bismuth-titannate as photocatalyst. And in the last graph, it shows the photoluminescence spectra in which we know that there are photorecombination activity. So here's the factors that affect photocatalysts. The first one is band gap energy. The lower band gap energy is better. And then the morphology of the photocatalyst. The uniform size and small size particle in the photocatalyst is more preferable. And then the last one is the recombination activity of the photocatalyst, in which the lower the recombination is the better. So our solution for our material is to lower the band gap energy, lower the recombination activities by doing incorporation of rare earth elements into our materials. And then we can also modify the morphology and size of our materials by doing synthesis using molten salt method. Why incorporation of rare earth elements can cause the lowering of band gap energy? Because we know that the A side of our material is bismuth ion, and we can replace it with lanthanum ion. Since the lanthanum ion has the bigger radius than the bismuth ion, it can cause the bond weakening on BO side, and then because of that weakening, it reduces energy splitting between valence band and conduction bands, and then it can reduce the band gap energy. And for the reduce of photorecombination, because incorporation of lanthanum or rare earth elements can capture the electron that already had in the conduction band and prevent it to be recombinate with hole that are exist in the valence band. So it reduces the photorecombination activity. Here's some evidence that uh, incorporation of rare earth elements improving the band gap energy. And here's we saw that we know that the incorporation of rare earth elements can also improve the photorecombination activity by reducing it. So let's talk about molten salt synthesis. It can modify the morphology of our materials, and the other benefit is because it's relatively simple. It requires lower temperature. It can increase homogeneity in our sample, and it can control particle size by varying the composition and using different kind of salt. And then it can also prevent agglomeration that usually occur in solid state reaction. So is it suitable? Because it can synthesize small and uniform particle size, and it's desirable for photocatalysts. And it means that the higher active area that we have. Here's the evidence that molten salt method has a better morphology than solid state reaction. In the life, we know that molten salt products has better uniformity in size and shape rather than the solid state product that's shown in the picture A. And from the graph, we know that that affect the photocatalytic activity because the solid state reaction product has the lowest photocatalytic activity compared to the molten salt one. So here's our objective after explaining all of that introduction. So we want to produce a material in which, in this case, strontium bismuth-titannate with better photocatalytic activities. By doing synthesis of strontium bismuth-titannate with lanthanum ion doped into it by using molten salt method. And to confirm the result, We use corresponding instrument and method to obtain the crystallographic data or something else. And here's the time and place that the research is proposed to, and then here's the material that we use, and then this the material that we use. The research, our research consists of three main stages. The first one is preparation and pre-treatment. The second one is synthesis of lanthanum top strontium bismuth tannate, and the last one is characterization of the product. First of all, the preparation of the and pre-treatment. First of all, we have to weigh the precursor accordingly, and then we put it on mortar agate and homogenize it for 1 straight hours. After that, we move the homogenized material into aluminum crucible and then heat it for 10 straight hours in the furnace with a temperature of 750 degrees Celsius. And we continue to the synthesis of lanthanum top strontium bismuth tannate by weighing the required salt accordingly and then mix it in the mortar agate with the pre-treated materials and homogenize it for 1 straight hour. And then we move the homogenized materials into the aluminum crucible. After that, we heat the homogenized material in the furnace for 5 hours on 850 degrees Celsius and 5 more hours on 950 degrees Celsius. After that, we put it out and let it cool. After the materials cool down, we put it in the filter paper and then we vacuum filter it using Purcell funnel and rinse it using warm water until there are no salts left. And then after that, we put the filtered product in oven with a temperature of 110 degrees Celsius for overnight. The last one is product characterization. The first characterization we use that is X-ray diffraction, in which the product is characterized using XRD, and the product and the obtained data can be investigate the from the data we can obtain the crystallographic data. And then the second one is characterization using SAM-ADS, in which we can obtain the morphology information and also the composition of each compound and each elements in our materials. And the third one is characterization using UV-based spectrophotometry, in which the data that we obtain is band gap energy. And then the last one is characterization using photoluminescence spectrophotometer, in which the data that we obtain can be useful to understand the photorecombination activity. And then after combining the all four data that we obtain, we can then conclude that is the material that we produce satisfies us or not. That's it. Thank you. That's all from me. Wassalamualaikum warahmatullahi wabarakatuh.